So we have an SO2 equivariant kernel with a stack of different spin filters, that is different m values, and we have a physical field which is also a stack of different ranked features, and both the kernel and the physical field that we're doing convolutions on can both be represented in this really nice simple complex exponential irreducible representation of SO2, or an SO2 irrep, and that unification makes the algebra really simple. So now that we're looking at a set of different spin filters in the kernel and a set of different spin values in the physical field, the way to really see what's going on is to write the tensor product, which really is just the way of organizing all possible couplings of all spins in the kernel with all spins in the field. Because a tensor product is just a tiling. You just couple every single element of the first vector with every single element of the second vector. So that's what our integral actually looks like. And so, so I'm using this explicit tensor product symbol here in the integrand just to make that explicit. And I'm going to drop the polar coordinates now just to simplify the notation a little bit. But as I mentioned before, we can have multiple radial filters in a given spin channel in the kernel. And we can also have multiple different features of the same rank, and they are another channel in the physical field. So I'm going to use indices C and D to represent these, and I use the word channel deliberately. So it's important to clarify that when we're talking about different m values, I'm going to refer to that as a different type. So spin types have spin m values, and then within a given value of m we can have different channels. That's exactly the convention used in tensor field networks, and so that's why I'm using it here. So really the integral needs to have two indices. It needs to have D and C to account for the different channels in the kernel and the different channels in the physical field, as well as the m values. And really what we want to do now is to understand what m values are actually going to survive in that feature map. So we want to know this mi tensor product mf in the superscript on L, which ones are actually going to survive the integration. And that's where the Clebsch Gordan coefficients are actually going to come to the rescue here, or at least the two-dimensional equivalent of the Clebsch Gordan coefficients. The reason that's, I say, coming to the rescue is because although the Clebsch Gordan coefficients make the algebra look more complicated, they actually simplify the situation because it means there are fewer integrals that we need to perform, because in the two-dimensional case, the Clebsch Gordan coefficients just act as a selection rule, and it tells you which spins actually survive the integration. And I'll show you that now. So firstly, let's just see how many actual integrations we need to do. So for this tensor product involving, what's that, 6 physical fields and 7 filters, so that's what, 42 integrals. And so, but just by showing the integrands here using this outer product representation for the tensor product shows just how many integrals there are to do, because it's, again, all possible couplings of all fields in the kernel and in the physical field, all spins, sorry, in the kernel and in the field. So the reason why Clebsch Gordan coefficients are useful is made really obvious with this sort of quick and dirty example. So let's say I've got this physical field V, and again, everything's expressed now in SO2 irreps, so I can just write it as a linear combination of complex exponentials. And the same goes for the filter. The filter, that is the kernel, does have a radial component, and it just factors out, as you'll see. Okay, so our integrand is just going to be V times F. And if we just write it as a sum for the moment, and we just add up, we just follow the normal rules of multiplying exponentials together, the exponents just add. Our convolution is just going to be expressed as this integral here. So as mentioned before, we need to use the complex conjugate when doing the convolution, because it's complex feature maps and a complex representation. And the algebra just comes out like this, right? So here's the key point. Most of these integrals don't actually survive, because for a given value of m out, that is for a different value of m for the feature map that you actually want, a lot of these integrals will just cancel and be 0. And that's because just this standard result, the integral of an exponential with I n theta is only non-zero when n is equal to 0. So only those integrals survive. For that reason, we can represent the final value of the feature map using this set of delta functions. So whichever value of m out you want, you use the delta function to filter out all the other ones. And that's why we end up with this selection rule: m out equals m in plus m for the kernel. So what I mean by that is that the spin value of the output, the feature map, is just equal to the sum of the spin value for the kernel and the field added together. And that's why we end up with this spin selection rule for SO2. That's what the Clebsch Gordan coefficients do in 2 dimensions. In 3 dimensions it's similar, it's slightly more complicated because it involves mixing, but it really just involves reducing the complexity of the computation, even if it makes the algebra look a bit more complicated. So let's just take a quick look at what those selections actually look like. The reason why the spins actually add up like that is just purely because the exponents just add up when you multiply exponentials together. It's that simple. And so you can see that there is some structure to it, and it just really purely captures the fact that, like I say, exponents add up when you multiply exponentials together. It's as simple as that. So we're in the position then to write our SO2 equivariant convolution, now accounting for different spin values in the kernel and different spin values in the field, using indices D and C to index the different channels in the kernel and the field, and with the Clebsch Gordan coefficients to filter out the zero integrals.